Analog front end in fact is an analog product that stays on the front end, so it means it's the first interface to the sensors. So in this case we are speaking about pH, so there are probes that are of course in contact with water and provides analog signals. These analog signals are very delicate, so that possibly the information that they are providing is easily corrupted by temperature variation, by interference, and so on. So you need a device that is able to convert these delicate signals into robust data.
Welcome to We Talk IoT, where we explore the ideas and impact behind AI-driven tech of the future and how data creates real business opportunities. To stay ahead of the innovation curve, subscribe to our newsletters on the FNet Silica website. I am your host, Ruth Haydock. Two billion people worldwide lack access to safe drinking water. Traditional pH monitoring still relies on manual sampling, with results often arriving too late. But with Edge AI, we could track water quality in real time at the source. Today, we are exploring how NXP's AI-assisted pH monitoring is transforming agriculture, municipal water systems, and communities without reliable access to clean water. My guest is Fabrizio Librizzi, Senior Product Marketing Manager at NXP Semiconductors. Fabrizio, welcome to We Talk IoT.
Hello, Ruth.
Thank you for joining us. Before we start diving deeper into the matter of water, what is it you do at NXP Semiconductors?
Yeah, I'm a product marketing manager for a family of products that are analog front end, dedicated to industrial applications. So we develop these products in order to bridge from analog world signals that stays in the analog to the digital. And then these digital signals goes into our microprocessor devices that then elaborate the data and with particular algorithms like, as you say, the AI or machine learning to provide data to our users.
Our topic today is water quality and everything tech can do to help make drinking water safe for everybody. I have researched, and the material you have provided, depending on how you define access and safe, there are 40% of the global population that do not have access to safe drinking water. Could you walk us through what traditional pH monitoring looks like and how an AI-assisted system changes this game?
Typically, to check if the water can be drinked or not, there are samples of this water that are being analyzed by laboratories. And then basically there is some time needed when you pick the sample water, go to the lab, and has been analyzed. Of course, the analysis is very accurate, but is slow, and the response time is slow. This means that sometimes the time the feedback goes to the people that should use the water is long, and then in the meanwhile you don't know, especially if there has been an event like a flood that has been possibly contaminated the water. So the time they receive the feedback, they can drink it, it's long. So that's a problem for those people.
And what led NXP to prioritize water quality monitoring? Was this driven by a customer, or how did this came about?
Measuring the pH is a typical application for electronic systems like, in fact, analog front-end chips and microcontroller. What is new is that thanks to the artificial intelligence at the edge, when I say at the edge, it means locally. So typically we think about, and especially we use artificial intelligence in our PC that is cloud driven. So our inputs goes to the cloud, that has been elaborated by the data centers and gave feedback to us. The AI at the edge means that the data is elaborated and an output is generated really locally where the input is coming, exactly at the same point. This allows to have a fast feedback from the machine learning algorithms or models to the people who are using this. So basically, this electronic system is able to decrease the time where you got the feedback and provide a reliable and continuous data output.
For our listeners who aren't maybe hardware engineers, what exactly is an analog front end and why does it work so well for this application?
Let's break the three words. Analog means, of course, that processing analog signals. Typically, our world is full of analog. So we know that every system or every quantity we observe is analog. So then, in order to be processed by PC or artificial intelligence, whatever should be converted to digital. So all the elaboration that we see is done on digital. Analog front end, in fact, is an analog product that stays on the front end. So it means it's the first interface to the sensors. So in this case, we are speaking about pH. So there are probes that are, of course, in contact with water and provides analog signals. These analog signals are very delicate, so that possibly the information that they are providing is easily corrupted by temperature variation, by interference, and so on. So you need a device that is able to convert these delicate signals into robust data. So this is done through an analog to digital converter that, in fact, convert the analog information to the digital world. And then at this point, after the data is digital, it's very robust. There are also algorithms that are able to secure this data is not being corrupted by electromagnetic interference, whatever. But then this is a delicate role the NFA has to convert small, delicate signals to robust data output.
Mm-hmm. And I think you already mentioned why this needs to happen at the edge, but maybe
yes.
Why not just send it to the cloud for analysis? I think you mentioned speed for one reason, but are there others?
Yes, speed is one reason. Another one could be sometimes these water sources are in a remote area where the cloud connectivity is not available or is intermittent. So having the information processed locally allows better resilience of the information provided, and also, as we can see, is a kind of also of equity. So people that where the networking is not available easily basically can benefit by this with on the edge artificial intelligence processing.
Mm-hmm. Yeah, terrific. I imagine that those are actually also the communities that are also hit the hardest by climate change and the consequences it has for water quality, right? So that it combines it really well.
Yeah. Also, for example, pollution is another element. Typically, polluted elements change the pH, alter the pH. So pH change can be also a first sign of polluted water, even if it's not deterministic, of course, but at least can raise the flag that something has to be subjected to deeper analysis in order to understand if something happened.
Okay, got it. And what does the machine learning model actually learn when monitoring pH levels? So you said it's an indicator that when these levels change, it could be a sign for pollution. Is it spotting patterns, predicting anomalies, or something else?
Typically, a machine learning algorithm is deployed in different phases. On the first phase, you put your system in a known system and you verify that the information is double checked with manual, of course, with manual checks as before. So you compare the result of your machine learning algorithms to the real data that you still measure with, let's say, traditional systems. So in the first phase, this is the learning path, the learning phase in which you teach your algorithm how to, let's interpret the data. Then, basically, typically, there is a trial where you install this system in several places, not so many, but just controlled place. And when the algorithm maybe is refined with a better data information coming from more sources. So it's a step-by-step process that at the end can provide better. And then, of course, after many systems are installed in the field, of course, there is a continuous improvement where the algorithms are always improved.
What are some use cases? I think I heard you already mention, of course, communities that do not have access to safe drinking water in general, but I think also agriculture comes to mind, or municipal water systems. Can you share some examples?
Yeah, for example, you said agriculture, of course. pH is important because we know if the pH is altered, also the water going to the plants can also create damage to the plants. Or industrial treatment, for example, in industry needs to control the water in their processes in order to provide any type of goods. Typically, water is heavily used by industries. And also municipalities, for example, imagine thanks to, if we think about these systems also with a certain level of connectivity, municipalities can provide transparent data to the peoples that show the pH level, the water quality level in real time, so can also provide a service to the people that stays in that municipality, for example.
We will take a short break. Stay with us, and we will be hearing from our guests very shortly. This podcast is brought to you by AFNet Silica, the engineers of evolution. Subscribe to our AFNet Silica newsletter or connect with us on LinkedIn. If you want to learn more about us, we have put information and links in this episode's show notes. What are the biggest technical challenges in ensuring that these electrochemical sensor readings are accurate?
Yeah, I already mentioned delicate signals that coming from the probes. That is the first, but this is, let's say, the key benefit of our analog front-end chip. But also, for example, sometimes the data coming from pH are what we call is a kind of data silos. So just those data. So having multi-channel, for example, information coming also from other probes, for example, temperature or humidity and so on, can allows of course data aggregation that again can be processed by the machine learning algorithms. So in this way, the data are more consistent because takes into account not only the single measurement but multiple measurement. For example, our NXP NFE has a multi-channel operation with temperature compensation that can provide the base for this type of use.
Are there any real-world examples you are allowed to share where you can maybe give some practical insight and also what problem this solved and what wasn't possible before?
Yeah, as I said, the possibility to allow the collection of data in remote areas, especially also considering that some of these systems can be also battery-powered, so allows to provide this kind of service in places where before was not possible. So that is the real use case. And as I said, also industry can benefit of that by having continuous monitoring of the water instead of having, let's say, episodic measurement from time to time, whether it's once a day or once per hour, whatever. This allows automation systems and also provides the possibility to have automatic decision. So whether to increase the chemistry, to correct the pH can be done real time. Also, for example, avoiding over and under dose Because if you do a measurement, imagine your pH is too much high. So you need to overdose the pH minus chemical in order to go down with the pH. If you have a continuous monitoring, you avoid overdosing, which means also reducing the cost of the chemicals.
Yeah, when I think about industrial applications or agricultural fields, to me it comes to mind that these systems also must operate in very harsh environments. How rugged does the hardware then need to be?
Yes, typically this hardware needs to resist to surge, for example. This is the most common source of, let's say, robustness that needs to have. So surge protection or electromagnetic interference protection needs to be taken into account. Of course, our NFE has been designed for that, so can resist in a harsh environment that is designed for this application, in fact.
Okay. And are there any limitations to what Edge AI can achieve in the field of pH monitoring, or are there cases where human oversight is still essential?
As we discussed, if the learning phase is done properly, so if you teach the system, you control in the learning phase the result, actually there is no limitation on that. So the data are pretty much reliable. The only, let's say, think that operators should do manually is because, probes sometimes have, of course, aging, the probe itself, or degradation. So the probe needs to be changed from time to time. So that is the source of information, and this cannot be done, of course, by this system. So the probe itself, which is the first source of information, has to be maintained properly in order to get reliable data.
What advice would you give water authorities or agricultural operators when they are considering this AI-assisted monitoring? Where should they start, in your opinion?
Yeah, that's also part of the step-by-step process of implementation. So what they can do is have one or two systems that they put under test. So they see the data coming out of the electronic system, compare the data with the traditional analysis they typically do, and maybe do this test for some time, maybe few months, to check the data are reliable, and then they can start implementing in their system. And also, especially for industry, it will be very important to have the connectivity, as I said before, so integrate this electronic system in their data information so they can have all at once the information about water as well in their dashboard.
Does it make sense to combine this information also with data from other sensors?
Yes, for example, temperature is the first one that came to my mind, but also sometimes information coming from the cloud, like weather. For example, as we discussed, humidity can make some difference in the measurement, or correlate the pH variation with weather events, like for example, if there is a particular, let's say, floods or drought, can influence, and so they can correlate the pH measurement with events that happens locally.
If you had to put together a soundtrack for this episode, what song would you put on it?
Yes, I was thinking about a song from a band called System of a Down, which name of the song is Toxicity, because it speaks about environmental problems. Because, for example, urbanization is another big urbanization area, put a lot of stress on the water quality for all the people. So this song is about urbanization and toxicity of our cities and so on. So that's what came to my mind.
Oh, that's a perfect fit. Terrific. Thank you so much. I will put it on our playlist.
Okay.
It is actually quite scary. We did have I think it's now actually a couple of years ago, we had a guest on the show talking about smart water metering, and he also shared some horrific numbers that in a couple of years, big major cities, and it doesn't even matter if they're from less developed countries, but even Barcelona, London, big mega cities like Mexico City, they will all run out of water. So this is actually really important work that you are doing, and that tech is delivering solutions for this. It will affect all of us at one point, right?
Yeah, sure.
Thank you, Fabrizio, for sharing your expertise. It was really interesting to see that Edge AI is now also moving beyond vision and voice into environmental monitoring that can genuinely improve lives. Thank you so much for being on the show.
Thank you. Thank you. Thanks a lot for the people listening to this. Thanks.
Thank you for listening to We Talk IoT. Stay curious and keep innovating. This was Avnet Silica's We Talk IoT. If you enjoyed this episode, please subscribe and leave a rating. Talk to you soon.